All right, our next speaker is Robin Shelton, Transformative Relationships, the interactions between high-velocity clouds and our galaxy.
So by way of introduction, I'm showing this image of the galaxy with a high-velocity cloud right here. This high-velocity cloud has a speed relative to the line of sight of at least 90 kilometers per second. And it's currently in the halo, where it's going to be interacting with the gas in our galactic halo. But over time, it perhaps will come down and collide with the disk, where it will interact with the disk. So by way of introduction, that's my way of saying I'm going to talk about those two interactions. Firstly, this interaction when the high-velocity cloud hits the disk of our galaxy, and then secondly, the high-velocity halo interaction. Do you want me to move it?
Yeah, just move it up.
Okay. So I'm going to use it as an example of a high-velocity cloud hitting the disk of our galaxy, the Smith cloud. And I got excited about the Smith cloud several years ago when I was talking with Jay Lockman, who is he's a Smith cloud booster, and he spread his boosterism to me, and so now I am too. Sorry?
Can we just use the podium if we need to?
Can you guys hear me now? Yes. Thanks. All right, so I think you heard the part about I'm now a booster because Jay Lockman was a booster and he spread his enthusiasm to me. So the deal with the Smith cloud is that it's at known distance, about 12 kiloparsecs from us, and that allows us to have a known mass, and it's a few million solar masses as a combination of H1 and ionized hydrogen. Jay used the gradient in velocity shown here in order to figure out the transverse velocity, and that plus its radial velocity allowed him to figure out its total three-dimensional space velocity and then do a toy model that allowed him to figure out what the trajectory of the Smith cloud would be. And I say toy model because he had to make the approximation that there were no hydrodynamic interactions between the Smith cloud and the galaxy. And that's clearly not a correct way to do it, but it's a great Physics 101 ballistic model. So here's the ballistic model. The Smith cloud is here right now. It's poised to move up and collide with the disk in the future. And if we follow its trajectory backwards, it's come through the disk in the past. And that's why it's our poster child for disk HVC interactions. Well, we know that there's going to be a collision here, but what of this collision here? If the Smith cloud has truly come through the disk of our galaxy, it's not likely to have survived that unless it had some help. And in the postulated help is dark matter. The postulation is that there was a dark matter subhalo in which the Smith cloud, with which the Smith cloud is associated. That dark matter went through the disk of our galaxy without incident, because of course the dark matter is dark matter and it doesn't interact with the galaxy in a hydrodynamic way. So it just came through the disk of the galaxy without incident and then gravitationally pulled the Smith cloud with it. So that's the hypothesis. I'm using this as just an example of what a collision would be like. So we wanted to see what that collision would be like, but I'm going to tell you also that the results that we have are probably relevant to for what this collision will be like, and what other collisions between high-velocity clouds and the Milky Way, or with disks in general, because there are high-velocity clouds around other disks, what those would be like. So we ran a set of simulations, and to give credit to predecessors, Nichols et al. Had done some hydro simulations. What's different about ours is that we include the magnetic field, and that we also use more realistic values for the disk, et cetera, et cetera. So we have 6 simulations here. These all have the same cloud, the same baryonic cloud as 5 million solar masses. So these 2 are cloud only. These 4 have dark matter. These middle 2 have dark matter of 300 million solar masses worth of dark matter, and the 2 on the far right have 1 billion solar masses of dark matter. All of them are going to fall through the disk. This is a realistic disk, and every other one has a magnetic field following Janssen and Farrar's coherent components of the magnetic field. We weren't able to put in the random components, and so our total magnetic field is actually quite weak. So now you're seeing them drop. And as these clouds hit the disk, there's going to be an enormous splash. That splash actually destroys the cloud. And roughly half of the cloud will end up in the splash material above the disk and a little bit below the disk. And the other half, approximately, will end up in this bubble that is forming below the disk. So the cloud, half above in the splash and half in a little column in the middle of that bubble. The remainder of the bubble, the periphery of the bubble, is actually disk material, which is cool if one wants to go about and try to observe this. The bubble is a cool bubble, and the edge is mostly disk material, so it should be filled with the metals of the galactic disk and with the dust of the galactic disk, which would really aid in observations. It's also an enormous bubble. Look at those sizes. You're at about 4 kiloparsecs right there. And it's very long-lived. It's larger in these cases that had a dark matter. It's very long-lived. We're looking at timescales of 50 and longer million years. What of the dark matter? What of the cloud? What has happened with the dark matter is that as the dark matter came through, it grabbed material from the bubble. It did not actually shepherd the cloud through. The cloud was destroyed. But there was a lot of material and a lot of material moving down that was in this bubble. The dark matter merely gravitationally grabbed that material. So the cloud that it's got down here is at least 50% disk material, at least. Okay? And if you're wondering, what about the hypothesis that got this started? What of these clouds? Are these sufficient clouds to be Smith clouds? My conclusion is no. And the reason is that these are tiny clouds. Those right here, they have a mass that's about 1/50th of the original mass that we put into the simulation. These over here are at best about 1/10 of the mass that we put into the simulation. So if one really insists that the hypothesis is true, that the Smith cloud has undergone this kind of experience, one would need an extremely large dark matter component. And that's 1 billion solar masses we put into it. One would need an even larger dark matter component in order to grab enough material to make up the Smith cloud that we currently have.
And that doesn't model how long ago did it pass through the disk?
Can I wait till the end? Because I think I'm going to run out of time. All right. So I have another whole section of the talk. So collisions with the disk are overly transformative. They destroy the clouds. But they make a very interesting bubble and a new cloud, which are interesting and are potentially applicable to other cases of clouds, dark matter dominated or not, colliding with our galaxy. And that should be happening more than once. Now, the second part is HVC-Halo Interactions. So let me back up. HVC-Halo Interactions, and this is a simulated high-velocity cloud that's gone through the halo and material has been blown back. Those simulations are done like this. We simulate a portion of the cloud. We like to put it along the symmetry axis so that we can say the other side is simply a reflection of the side that we do simulate. And we also sometimes do this, we like to do it in the reference frame of the original cloud so that we can have the halo gas blow past the cloud. So as you know, life is seen from the cloud's point of view. What happens in this case is that material gets ripped off of the cloud, gets bladed off the cloud, becomes part of the halo. This eventually slows down and becomes part of the halo. And it's a significant contributor to the halo in the sense that a significant fraction of the oxygen-6 that has slowed to normal halo velocities can be contributed by the population of high-velocity clouds in our galaxy. At the same time that the cloud is sharing with the halo is sharing with the cloud. It's a two-way street. Material is being entrained by the cloud. So halo material is joining the cloud. Its velocity is being accelerated to the cloud's velocity, and it is actually cooling down to the point where we can find material that is 10,000 degrees and less in the cloud at cloud velocities that originated in the halo. This plot shows you some applications. One application of that is the metallicity of the cloud. The effort to figure out what the metallicity of observations of the metallicities of clouds have been used to try to figure out where clouds came from. And what I'm telling you here is that the observed metallicity is not really the true metallicity of the pristine cloud, but it's rather a combination of the cloud plus the entrained material. Okay, so you're seeing panels. Let's look at the ones on the right. These are in time. These are epochs in time. That's 0 million years, 40, 80, 120, 160, 200 million years. This panel is showing you the fraction of gas that is from the halo. So it's color-coded, with red being 100%, 0 being 0%. And you're seeing all sorts of colors like that yellow. Let me just point that one out. That's roughly 70%. Meaning that's stuff that looks like a high velocity cloud. In reality, it's 70% halo material that's been pulled in. Okay, there's a gradient across the cloud from the head back through the tail. That gradient starts at low amounts of entrained gas, ends up at high amounts of entrained gas. That same gradient is also a gradient in temperature, and it's also a gradient in ionization level. But again, let me say, we see some gas, some halo gas can cool, and so you can end up with cool halo gas, and you can also end up with recombined halo gas. So you actually can get, say, for example, oxygen 1 that has come from the halo. So the effect is most pronounced in ionized gas, but it is also present in neutral gas. We get up to, say, 20% of the oxygen 1 being due to the halo. We apply it to the Smith cloud. Again, my enthusiasm for the Smith cloud coming from Jay Lockman. So here's a picture of the Smith cloud. Here are 4 directions whose metallicity has been sampled. And what we're telling you is that the simulations will say this end is most pristinely cloud. This end has, in our cases, for these distances, well, this end here has about 50% halo gas. And I'm picking that number because we looked at the size of the Smith cloud, we looked at the directions of these observations, and for sight lines that go through our simulations, even at the direction and the angle of these observations, we get roughly 50% entrained gas. So if the Smith cloud is extragalactic, you would expect a low metallicity here and for it to increase as you come back. If the Smith cloud was made in our galaxy, and if the halo it's gone through has a lower metallicity than the region in which it was made, then you'd expect the gradient to go in the opposite direction. Okay. How does that compare with the observations? If we look at this direction, and this direction, the observations, this line of thinking leads to the idea that the Smith cloud is extragalactic and is picking up metals from our galaxy. The difficulties in this, and again, we're still in preparation, the difficulties are that this observation surprisingly has a low metallicity, and that the error bars are enormous. Take a look at some of those numbers there. Here's a metal abundance of 0.53 plus 0.44 minus 0.15. So the error bars are really large. And so I think this is a case of a theorist saying, I support observers in going and taking more observations of this object. All right, so in summary, high velocity clouds that collide with our galaxy, with the disk, destroy the cloud as they blow bubbles, and the dark matter can accrete some material, and high velocity clouds traveling through the galaxy shed material and entrain material. And I want to give photo credit because I thought this was so cool. This is Transmorgify melting ice cream bars. There we go.
I enjoyed your talk very much. But actually, the cloud you showed as falling down to the galactic disk is only the Smith cloud. Is that correct? Maybe if you could tell us a few more cases of similar falling down clouds, that would be very better, much better.
Okay, so you're saying I've only applied it to the Smith cloud and you want more examples. Is that your question? What about complex C? Complex C appears to be angled towards the disk like this, where one part of it is closer to the disk. That part is also closer to the inner galaxy. So that seems to be something that is falling into our galaxy. What about the leading end of the Magellanic Stream, which has come up through the outer part of our galaxy? And complex H.
And then we'll go across. Okay. We're not going to be able to get to everybody, but go
Nice talk, Robin. Complex C, I think, has the wrong gradient, though. You might want to look at that, the metallicity gradient. But my question was actually on the reaccretion of gas as it goes through the disk and the dark matter. Have you thought about this explaining the multiple stellar populations seen in dwarf galaxies?
No, thank you for that great idea.
Yeah, because they've been going on about it being somehow they're reaccreting gas, but doing that is not easy. But you have a nice model for how that could be done.
Okay, thanks.
Hi, maybe this is a trivial question, but it's inspired by this ice cream here. So I was wondering what is the time scale for thermal evaporation of these clouds compared to their trajectory, the time they take to crash into the galaxy, and if this is significantly modified by the magnetic field.
Good question. There's been some work on that. Let me just go back to give a visual for that kind of thing. So this cloud is ablating away. There's been some work on this. Heiles and Putman beat us to it, and they did hydrodynamic models, and they found timescales dependent. There's a relationship between the size of the cloud. But to give you, and we then followed up with some work, Kwok et al., and we also found the timescale. So you're looking at roughly 100 million years timescales. My graduate student, Jeff Gritton, is working on larger clouds, and he's finding they survive longer, as you'd expect. You asked about magnetic fields.
Yeah, I expect that to change. I mean, it will be much longer in the presence of the magnetic field.
I agree. The simulations are showing you that too. If I remember correctly, the Heiles and Putman were purely hydrodynamic. Most of the stuff we did with Kyujin and Kwok was hydrodynamic. Jeff Gritton has done a bunch with magnetic fields. And the magnetic fields are really interesting. They form like a protective layer in a way around the cloud, but also they change the effectiveness of Kelvin-Helmholtz instabilities. And so the clouds are able to survive much longer.
Just one more question right there.
Good job. So if the talk had been in the reverse order, I would have been totally convinced this was an extragalactic cloud with all that. But the first part of the talk, I thought.
You convinced us that that couldn't be right, because in the first part of the talk, you showed us that trajectory, it had to go through the disk, and the disk would have destroyed it. So how do you reconcile that?
How I reconcile this is, my suspicion is that if I were to guesstimate the trajectory, it's that the cloud probably has just come in like this and has been slowed during its entry into the galaxy and then is heading out. That's my guess.
Okay, let's thank Robin one more time.
Thanks. Can I let you do the